This is Spiro, and this is my pseudocode for matrix multiplication. So before I get into the actual code, I'm just gonna go over a little bit about matrix multiplication. In order for matrices to be multipliable, I guess, here I have set up matrix A times matrix B. In order for them to be compatible, the column numbers of A has to be equal to the row numbers of B. But the row numbers of A do not have to be equal to the column numbers of B. And in fact, our product matrix will have the dimensions of rows of A and columns of B. That's basically what I just wrote here. So in order to find each individual matrix point's product, new value, what we do is we take, so we'll start in the top left of this matrix. Here we're multiplying a 3x3 matrix, meaning our product matrix is going to be 3x3 as well. So for our top left point of our new matrix, that is going to be equal to x1 here times this x1, y1 times this x2, z1 times this x3, and the intersection of these two blocks, so the top left, that's the location of the new point. So that's what I wrote out here. That top left point will be equal to that value. So basically, now to get into the code, the first thing we have to do is to check that the column numbers of A are equal to the row numbers of B. If they're not, then I just bring them back to retype their matrices. If it's true, I'll define a new matrix that has the row numbers of A and the column numbers of B. Then after that, I have to index through every single point of my new matrix to find each one's individual value. And that's what I have set up here. This is just the basic index through a matrix, double for loop, nested for loop. So I have I equals 0, j equals 0. This goes to the numbers of rows in our new number of rows in A, which is also the same number of rows in my product matrix. Same thing goes here, j, number of columns. So basically, I is going to tell us what row we're on, and j is going to tell us what column we're on. Inside of our j for loop, that's what this box represents, I'm going to have this in there. So I'm going to have another index, another for loop that says for k equals 0, k number of columns in our product, which is also equal to this. These are interchangeable, but I just wrote it here for clarity. For k to here, this basically just stops it from going outside of the number of rows of the matrix. It just keeps it within the matrix. I do product ij, our current index point, where we are currently in the matrix, is plus equal to, so it's going to add this value to product ij. So I have a matrix here just set up. I'm going to do a 3x3 matrix. Pretend we're multiplying a 3x3 matrix by a 3x3 matrix just to keep it simple. Basically, this says product I and j. Those both start at 0, so we're right here for right now. That is plus equal to aik times bkj. So what that will look like, I have red will represent A and blue will represent B. What that'll look like is, so we're starting here for our product matrix. What this is doing is it's going to start and say, hey, okay, for A, pretend this matrix is A right now. For AI, which is 0, I is not going to increment until everything else inside of it increments. For AIK, which would be right here, we're going to multiply that by BKJ. J is also 0. It's not going to implement until K is finished. So it's going to also stay the same. But K is going to keep going. So in our first pass through this loop, we're multiplying the location the top left values of both these matrices. And then after this goes once, we'll go, okay, now we're going to add to this, remember the plus equals, we're going to add to this, now k is equal to 1. We're going to add to this I, which is still 0, that hasn't changed, ik, but now k is 1. So now it's here. We're going to multiply that by k, which is 1, here, this row down here. We're going to multiply that by j. Sorry, k1, j0. J hasn't changed yet. So we're going to multiply these two together, right? And then it just follows that pattern. And it's going to multiply these two together and add it. And then the sum of all those products is going to be our new top left point. And after that, once k hits the number of columns, which should be here, it's going to go all the way back up top to our first for loop. I is going to increment, j is going to increment, and then we'll be here. And it's going to repeat that process. It'll be this times this, and then this times this times this, and it's going to add all those products together, and that will be our new value for this location in our product matrix. And basically it just goes through our product matrix one by one and finds a new value for it. Quick little recap. Basically, we check and make sure that the columns of A are equal to the rows of B. If they're not equal, they retype it. Then we make a new product matrix, which has A's number of rows and B's number of columns. Then we index through the matrix pretty much. Empty matrix, that matrix is empty. We go through it, go to each individual point, and say, hey, this is going to be equal to this times this, and then we add it together, just how you would in matrix multiplication. This is Spiro Cromwell, and this is my pseudocode for solving simultaneous linear equations. So we use Cramers rule to solve for x, y, and z. And before I get into like the actual pseudocode, I'm just gonna go over how I got to where I am with my pseudocode. So the process for solving these equations involves like matrix determinant stuff. So basically we have our three equations here, 1, 2, and 3. Each of them have an x, y, and z variable with different subscript based on their equation, and coefficients for each. So c is the coefficient for z, b is the coefficient for y, a is the coefficient for x, and these are all equal to a d value. And if we were to put these coefficients into a matrix, it would just look like this. So this column represents x, this represents y, this represents z. So the first thing we got to do in Cramer's rule is find the determinant of this 3 by 3 matrix. So the way you do that is you take one of the top values. So I'll start with A1. So first I will eliminate these columns. So A1 we put on the outside, and we multiply that by the determinant of our new 2 by 2 matrix, which is this right here. And the determinant, you get the determinant of a 2 by 2 matrix by multiplying this together and subtracting the product of those together. And basically I wrote that all out down here. That's what this is. For our next term in this equation, basically instead of going from A1, we just go from B1. So we do this, and we use the remaining values, A2, A3, C2, C3, right here in our new 2 by 2 matrix, find the determinant of that, and then we add, following the same process, we add the C1 values determinant. So that gives us the determinant of our 3 by 3 matrix in its like normal state, and we can derive this equation from it This is the equation I use later on to solve for it in my code. Then after that, we got to find dx, y, and z. And this is the exact same process, but for each like corresponding variable, we replace that column with our d values from this equation. So to find dx, we'd take column 1, and we'd replace all those with our d's. And then it's the same equation here above, but instead of, our x values there, we just replace them with d, and then we get an equation that looks like this. So to find dy, you just replace this column with the d's, and to find dz, you'd replace these with the z. With the d, and it's the same process. Each of the equations is a little bit different, but same idea. And then after that, to get x, y, and z, you just divide dx by d to get x, dy by d for d or y, and dz by d for z. So now onto the pseudocode. So the first thing we're going to have to do is get user input. I'll have matrix A equal our coefficients and B be our products. So starting with A, we'll just do a nested for loop to index through each segment of the matrix. And we'll just ask, what is row I, column J of matrix A? We take the input and we store that in row I, column J of matrix A. Pretty simple, what we always do. And then this is for B. So B is a one-dimensional array, so we only need one for loop. We just ask, what is DI, which is the same thing as asking it, what is column I of B? So basically, it's going to look like, D1, D2, D3, and just go through it and take a user input and put it into there. Pretty simple. So then after that, after we get the user input, it's pretty much just following the Cramers rules process. So first we'll probably do this before the for loops, but we have all our variables here, and we just got to solve for them. So for D, to solve for D using our code, it's this equation here, the one from earlier, but instead of having A, B, and C, I just replace it with the location of each of those corresponding values in the A matrix. So for example, if you look at our equation, we have A1 times all this, A1 in our matrix A in our code is A00, and then B2 right here is A11 right in the middle. And it just follows that same process. It's the same exact thing. I just had to format it for like coding, you know what I mean? And then all this stuff here, to find dx, dy, and dz, it's once again the same exact equation, but where we replace our d values, so for dx we're going to replace all of our a's with the d values. Anything in column 0 of our A matrix, we just replace with B0, B1, B2, B3, so B0, B1, or B2. Same, but it's the same exact equation. Nothing's really changed. It's just basically simulates having this matrix without having to make a new matrix. Then we just follow that process for dx, dy, and dz. And then after that, we just do x equals dx divided by d, y equals dy divided by d, and z equals dz divided by d. And that should solve for x, y, and z.